So, so we're going to finish up the problem we were working on yesterday, which is the last problem that we're going to work in this chapter. So the chapter 2 test will be next Tuesday. I'll I'll post a review video either today or tomorrow. Yes. You don't have that handout? Oh, were you here? You weren't here yesterday, were you? Yeah. Uh, I didn't bring one with me, but you can get one after class, and then you can ask somebody to help you during study session. Oh, you don't have one too? Yeah, I forgot to bring my papers today, so I'll I'll bring one up to you in study session, or a couple of them up there. Just look off your neighbor just to get an idea of what's going on. We were almost finished. Okay, so the problem was somewhere here. Well, where did it go? Let me reopen this file. I must have accidentally cut something. Yeah, so that's the problem. Some guy's fishing. He's reeling in his paper, and then it disappeared again. Oh, here it is. So he's has a fishing line, which the tip of the pole is 10 feet above above the water, and he's reeling in the fishing line. So the rate of change in the length of the fishing line, which is and the fish is right there on the surface. Okay, so we're not. So as he reels in the fish, ultimately it will dangle straight down, and then I guess he would reel it up out of the water in this case. So what we were doing is, with related rates, we have to use geometry somehow or another. And you might be tempted to use the Pythagorean theorem, but because they asked for the angle is not involved in the Pythagorean theorem, just lengths. So that would say, oh, we can't use the Pythagorean theorem, we must use some other relationship. And so what we used was this relationship, that the sine of theta, this angle, is equal to the length of the opposite side divided by the adjacent side. This height stays the same because the distance between the end of the pole and the water stays the same. What's happening is this thing is getting shorter, which is making this angle larger, and it'll approach 90 degrees as we finish reeling the fish in. So with this geometric relationship, we used implicit differentiation to take the derivative of both sides. And because we're taking the derivative with respect to time, the derivative of the sine was the cosine, but you had to add the d theta dt part to it. Likewise over here, we rewrote this instead of 10 over x, we wrote that as 10 times x to the minus 1 power. Use the power rule to get that derivative, but because it's implicit, we have x here and t there, we had to add the dx dt. So what that allowed us to do once we clean things up is have a relationship between d theta dt and dx dt. And all we had to do at this point was to figure out, we needed to know what the cosine of theta was. So we were going to use the Pythagorean theorem there to solve for the y length, which is this length. When this length is 25 and this is 10, so you'll need to do that. And then you can use the definition of the cosine, which is the adjacent over the hypotenuse, to find the cosine. So that'll give you that number. X is 25 feet, and dx dt is negative 1 foot per second. So all you need to do now is finish it off. So solve for d theta dt and plug in this stuff. So if we take that equation that relates the rates and just solve for the unknown, which is d theta dt, it's going to be equal to negative 10 over the cosine of theta times x squared times dx dt. So go ahead and finish that. I'll give you a few minutes to get ahead. Start. And the angle, the d theta to t, is going to be in radians. You could change it to degrees by multiplying by 180 and dividing by pi, but they didn't ask. I don't think they specifically asked what units, so we would just assume it's radians per second. And the angle, what do you think the angle should be? Just a guess. Don't without using your calculator. It's going to be, sine is going to be, yeah, that's not a very accurate picture, I don't think. Right? It's probably a lot lower angle than it looks like in the graph, because you have, remember, the sine of 30 degrees is a half, so that's going to be a little less than a half. 10 over 25 is going to be what is it going to be? 0.4. So if the sine of 30 degrees is 0.4, then, I mean 0.5, then it should be around, what, 23.79, no, just, it's going to be 20 some degrees, I think. That's my guess. So you can't always trust the drawings that they are accurate. Well, the cosine, well, yeah, what you need is the cosine. So, but you don't have to actually calculate the cosine. You just take the ratio of these two. So you've got to find y. Oh, the cosine is going to be probably more like 0.9 something, but the sine. So what you do is you calculate y from this equation, plug it into here. So you never actually have to use the cosine function on your calculator. What you can do is, you theoretically you could find out what the angle is and then take the cosine of that angle. So that would be allowable. Or you can do it this way, which is not actually ever finding out what the angle is. You can just find out what this other length is and then find the cosine. So either way is okay. But if you do, so I think what you're asking is another way to find the cosine would be to find the angle theta, which would be the inverse sine of 10 over 25. And yeah, so I'm telling you what the angle is, but ultimately you don't need to know that to solve the problem. So once you calculate theta, then you can take the cosine of theta, and you'll get the same answer, whichever way you do it. We'll demonstrate that is true. Inverse sine of 10 divided by 25, which is 23 point, that was pretty close, 23.6 degrees. And then you could, oh wait, sorry, that's theta. So theta is equal to 23.6 degrees, and then you take the cosine of that, which is 0.917. So that's one thing you could do. The other thing you could do is if you solve for y here, you'll get 25 squared minus 10 squared. Take the square root. So you get y is equal to 22.9. And then you could plug it in here. 22.9 divided by 25 is equal to 0.917. Same thing. Okay. Of course that's right. So those are the two ways you could get the cosine of theta. You could use the inverse sine to get theta and then take the cosine of that, or you could use the Pythagorean theorem to get the adjacent side and then use the definition of the cosine. This way you don't ever have to know what theta is. You just need to know the cosine of theta. Okay, so let's plug some numbers in here. So I got 0.017 radians per second positive. And that makes sense as this gets shorter, the angle should get larger. So the sine makes sense. So as you shorten the hypotenuse, the angle gets larger. Also, from a unit standpoint, you've got feet times feet divided by feet squared, which leaves just inverse seconds. Radians don't have units, so because it's an angle, you put in radians. I mean, radians are feet per feet. It's the length of the arc divided by the radius around a circle. So there you go. That's the answer for that one. Okay. I already assigned the homework right for this section, so don't need to do that again. So we're going to move on to chapter 3 now. So test next Tuesday on chapter 2. There'll be one related rates problem. So you probably need to know how to do related rates to get an A, but if you have no idea, you could still pass the pass the test. Okay, so chapter 3 is called, I think it's called Applications of Derivatives, something like that. Applications of differentiation. So we're not going to learn any new differentiation techniques, but we're going to use the derivatives for a number of different tasks. So I'm going to write the things that we're going to learn in this chapter, just to kind of give you an idea of where we're going. So we're going to use differentiation to figure out where you have local minimums and local maximums. You should know somewhat of what that is from pre-calculus. But if you forgot, if you have a curve that looks something like this, like a third order polynomial, this would be a local maximum, because if I go to the left or right, it becomes less, and this would be a local minimum. So the key thing about minimums and maximums are that they have zero slope. So we can use that if we can figure out what the derivative is and set it equal to 0 and find out the values of x where that happens, we know where we have maximums and minimums. So that's one thing we're going to do. Another one is what's called looking at curvature. And curvature is, for example, this one up here. This is curving. If you think about driving a car, and this would be the inside of the curve. And then if you then turn the other direction, made a left-hand turn, this would be the inside of the curve. So you can use the derivatives to figure out which way a function is curving, whether it's curving down or curving up. And both of these can be used for sketching graphs. So back in pre-calculus, to sketch or to draw a graph, especially polynomials, the only tools we had were to look at the end behavior, whether it goes to plus infinity or negative infinity at the ends, where the x-intercepts and y-intercepts were. There's one y-intercept, there's maybe one, maybe three x-intercepts. These two things, the first two things, allow us to draw much more accurate sketches without having to plot them. Now, in the old days, before calculators and graphing calculators and computers, you couldn't just put the equation in a program and it plotted it out. We're so used to that. We put it into our graphing calculator and say graph, and there it is. So the ways that you could do in say the 60s and 70s is you could just pick 20 points and just find the x and y values, pick 20 x values, calculate the y values for the function. Which, if it's a polynomial, that's not trivial either, because you didn't have calculators, so you might use a slide rule. So just the process of plotting 20 points, calculating 20 coordinate pairs, and plotting them was difficult. And if you pick the wrong 20 points, then you'd have to pick 20 more points. So there was a lot of things that you could use calculus for sketching graphs to find out where minimums and maximums were. Those are probably the most important parts on a curve, besides finding where the x and y intercepts are. Nowadays, because we have graphing programs and we have graphing calculators, it's not, that part of calculus is not as valuable as it was, but we're still going to learn how to use it, just to give us a general idea of what the key things are for different kinds of functions. So we'll learn how to do sketching graphs using the minimums and maximums and curvature. And we'll talk about optimization. So this is actually why this whole chapter is why Zane's taking this class, because he's taking business. He's going to be a business major. Where are you going anyway? I forgot. Tech? Okay. I thought you were. So optimization, if you're trying to maximize for business, maximize profit, minimize cost, and if you can mathematically model the process, the business process that you're looking at, then you can use math to figure out where you have those points, how many of a certain thing do I need to make for a certain size factory or whatever it is. You would use calculus to do that. And it's the whole idea of optimization. And optimization is kind of like related rates. It's a lot of word problems. It's figuring out what's to do. So we'll get to that. And then there's the last thing. Again, it's not as useful as it used to be, but it's a method for finding x-intercepts. It's called Newton's method. And one of the things back pre-calculus, you were given some function, y equals x cubed minus 2x squared plus 7x plus 3 or something like that. And if it turned out to be a rational root or rational intercepts, then you had techniques to figure out what they were. You might guess there's multiple, what are the possible rational solutions to this, where this goes to 0. You want to know where it intersects the x-axis. So you might say, well, it could be plus or minus 3. It could be plus or minus 1, just by using the rational zeros test. But it's not always a rational number. And so how do you find these x-intercepts without just kind of guessing and saying, okay, I'm going to pick this x and see what the value is, and I'm going to pick another x and see what the, you could just do it by trial and error to come up with where the x-intercepts are. You can use the slope of the line to help predict where the x-intercepts are, and it's just a quicker way of getting to the x-intercepts. They're not the ones that are not easy. Okay, so that's basically what we're doing in this section, is using derivatives to answer various questions. Okay, so here is kind of, we just talked about it. If you have this is a third order polynomial with a negative x cubed, and how do I know that? How do I know that it's negative x cubed instead of positive x cubed? What is it about the shape of this thing? Yeah. If you have a positive x cubed, it starts down here, and it'll come up. It doesn't have to have the minimums and maximums, but it does have to start down here and end up going up this way. So because it's negative x cubed, it's going to start at positive infinity, do some things in between, and then go to negative infinity. So a lot of times with third order polynomials, you have these like little valleys and you have little hills, and this we would call a relative minimum. It's not the minimum is negative infinity, and the maximum is positive infinity. But local to this curvature, this is the local the relative or local minimum for that function. And likewise, here at this point, you have what's called a relative or a local maximum. One thing you'll notice is if you looked at the slope of the curve, it's negative at this point. If I drew a tangent line to this curve, it would be negative, and then it would become less negative, and then it would go to 0, and then it would become positive slope, then it would go to 0 and negative slope. So one thing too is where you have a relative minimum, you go from negative slope to positive slope across that minimum, and when you go from across a relative maximum, you go from positive slope to negative slope. So those are just observations right now. We'll formalize those in terms of derivatives in a second. So there are certain x values associated with functions that we give a special name, and they're called critical numbers. Critical numbers are x values. X, not x coordinate. Well, I guess it could be x. It's the x values, and it says, so here's the definition. Let f be defined at c. So c is some value of x. It says if f prime of c is 0, or if f prime of c is not differentiable at c, then c is a critical number of f, the function. So I've got two graphs here, one that has a cusp, one that just has a normal maximum. So, if I said x equals negative, let's say 3, which is here, is that a critical number? No, because the slope there is not 0, and it's defined. How about positive 3? Here's x equals positive 3. Come down to the curve. No, the slope is not 0, and it's not undefined. I come to this point, because it's a cusp, if I look at this, what it turns out is the slope goes from positive to negative. So right at x equals 0, in this case, the slope is not 0, but the derivative does not exist. The derivative exists here, and the derivative exists there. But when you get to here, where it's like trying to balance something on a knife edge. There's no, it's not like you can do that. So this is the critical number, x equals 0, of this function, because the function is defined, but the derivative is not defined. There aren't many functions that have this behavior, just a few. Most of the ones that we'll be dealing with are the second case. So at x equals 2, I think x equals 2, you can see that the slope of the tangent line is 0. So f prime of 2 is 0. Because that's true, x equals 2 is what we would call a critical number. Now, as you can see here, just because it's a critical number doesn't mean that there's a third example, like vertical asymptotes. At a vertical asymptote, the derivative does not exist, but it's not a critical number. Actually, it is a critical number, but it doesn't necessarily mean that you have a maximum or minimum. So at critical numbers, you might have a maximum or minimum, but it's not guaranteed. So yeah, vertical asymptote is a critical number as well. It turns out that it's not. In both of these cases, the critical number was a local maximum, but it's not always that case. So here is the relationship between relative extrema. It says relative extrema only occur only at critical numbers. If a function f has a relative minimum or maximum at x equals c, then the c is a critical number of f. So for there to be a minimum or maximum, it has to occur at a critical number, but it doesn't mean that a critical number is going to be a minimum or maximum. So what that means is if we find the critical numbers, those may or may, if there's any maximums or minimums, they're going to occur at critical numbers. But just because it's a critical number doesn't mean that it's going to be a minimum or maximum. We have to use another technique, which we'll learn about in the second section, to figure out whether at critical numbers, whether they are minimums and maximums or something else. The something else is usually that they're a vertical asymptote, which means that they're not a local maximum or minimum. But that's so it's not the converse of this or the inverse. Converse, forget which one it is not true of this statement. Okay, so what we're going to do is just how do you find the critical numbers? And the ones that we're going to deal with mostly in this chapter are polynomials, which are easy to differentiate. So the differentiation, for the most part, is going to be reasonably easy. We're going to also deal with trig functions, which are not so easy. So half of it's easy, half of it's not so easy. So to find the critical numbers, you take the function, and I went ahead and multiplied this out just to make it easier to take the derivative. You take the derivative, you set it equal to 0, or see if so you find out whether there are any places where the derivative is 0 or the derivative does not exist. Those are critical numbers. Now what I have here is that we're asking this question not for the entire domain of this function, but for the domain from -1 to 5. So sometimes we limit the x values that we're going to look at. So this is valid for all values of x. We're just going to answer the question between these two values of x. Okay, so step number 1 here is take the derivative. So f prime of x is just going to be 3x squared minus 6x. Where is the derivative equal to 0 or undefined? So that's where you have critical numbers. In this case, the derivative is a polynomial. The derivative of a polynomial is another polynomial. So this exists everywhere. So we can say one comment is f prime of x is always defined because it always exists. So there are no critical numbers associated with this derivative being undefined. The second case is we set the derivative equal to 0, and this involves factoring. So we factor this. So one way of factoring it is to take out a common term, which would be 3x, and that leaves x minus 2. I think I did that right. Okay, so in this case, we don't have to do any fancy factoring. We notice that there is no constant term, so we can factor out at least x, and we have common factor of 3. So therefore, f prime of x equals 0 when x equals 0 and when x equals 2. So what we can say is, and let's see, are those in the interval? Check the interval. So the interval was from -1 to 5. So both of those are in this interval, so we're going to count those. We have critical numbers at x equals 0 and x equals 2. That's it. Okay, so you take the derivative of the function. Ask the first question, are there any values of x in the interval where the derivative is undefined? In this case, no. Are there any values of x where the derivative is equal to 0? Find the roots of the equation. In this case, that was just simple factoring, and found that there are two values of x which are both in the interval that was defined for the problem. And because the derivative is 0, we can say that those are critical numbers. Okay, so pretty straightforward for polynomials. So here's one that's not a polynomial. We go through the same process. This is for t greater than t less than 3. Because if t is greater than 4, you're going to get a negative square root. So all this does is just make it so that this function is defined in this interval. So what we do is, step 1, take the derivative. So we'd have to use the product rule. So since I'm going to use the product rule, I'm going to change that to h, just so I can call the other stuff f of x, f of t, and g of t. So we'll say that f of t equals t, and g of t equals the square root of 4 minus t, which is 4 minus t to the 1/2 power. Okay, so those are the two parts of the product. Then you take the derivatives of those. So the derivative of this with respect to t is 1, and the derivative of this with respect to t is going to be 1/2 times 4 minus t to the minus 1/2 power. And just one more space, times negative 1. So I actually use the chain rule here because I have something raised to the 1/2 power. So this part would be f of u would be u to the 1/2 power, and u of x would be 4 minus t. So what I did, so that I didn't have to write the whole thing out, is I said, okay, take the derivative of this. I take the exponent, multiply it by the original expression, raised to the power reduced by 1, and then multiply the whole thing by the derivative of what's inside. So the derivative of 4 is 0, and the derivative of negative t is negative 1. Okay, so that's the chain rule to get that part. So let's clean that up a little bit. So g prime of t is going to be negative 1 over 2 times the square root of 4 minus t. So what I did there was the 1/2 just becomes a 2 in the denominator. This moves to the denominator, so it's 4 minus t to the positive, it becomes 4 minus t to the positive 1/2 power in the denominator, and then I rewrote the 1/2 power as the square root. So that's the derivative of that. So now to find h prime of t, which is the product, you take f of t times g prime of t plus g of t times f prime of t, and we just plug the stuff in there. So f of t is t, g prime of t is negative 1 over 2 the square root of 4 minus t, and then we add g of t, which is the square root of 4 minus t times f prime of t, which is 1. So that's the derivative. So let's clean it up a little bit. T goes up there. T divided by 2 square root of 4 minus t plus the square root of 4 minus t. So all I'm doing so far is I'm just taking derivatives. I haven't set anything equal to 0. So that's part A. Part B is is to, or part 2, I guess, is to ask the question, where is the derivative equal to 0 or undefined? Well, this would be undefined at any value of t greater than 4. If t equals 4, you get 4 minus 4, which is 0, and you get this divided by 0. So that's undefined. But it's not in our interval that we talked about in the problem. The interval was for t less than 3. So we don't have to worry, that would be one place where the derivative is undefined. But in the interval that we're looking at, it is defined. So there's no, if I have, say, t equals 3 or t equals 2, you're going to get a positive number here. You get a positive number there, and you'll get a positive number there. Just they're all numbers. So there's no place where within the interval where the derivative is undefined. The second case is where that derivative is equal to 0. So let's add a page here. So the second part of step 2 is to set the derivative equal to 0. Like that. So the question is, what values of t does that go to 0? So probably what I would do is I would multiply the whole thing by the square root of 4 minus t. That way I get rid of this in the denominator. And when I multiply 0 times that, I get 0. So this still stays 0. And then I'll end up with negative t divided by 2, because this cancels out. And then when I multiply the square root of 4 minus t times the square root of 4 minus t, I get 4 minus t. And I could multiply both sides by 2. That would give me negative t plus 2 times 4 minus t. And then I multiply everything out. Negative t plus 8 minus 2t. So I get negative 3t plus 8 equals 0. 3t equals 8. T equals 8/3. Okay, so that's me solving for the values of t where the derivative is 0. There's one value of t. That is in the interval. So remember, the interval says it has to be less than 3. This is slightly less than 3. So because that the value of t where the derivative goes to 0 is within the interval, this, what we can say is, what was the other question? What was the other step? Okay, so we answered this one, said within the interval, defined, the derivative was always defined. We found out that x equals 8/3, that the derivative is 0. So that's where I'm checking the interval. Yes, it is within the interval. And therefore, so we can write that down. So step 3, yes, 8/3 is in the interval. So it applies to this particular question. And therefore, number 4 says, therefore, we have a critical number at t equals 8/3. So there's one critical number. Now, if there is a minimum or maximum, it has to occur at t equals 8/3. It may not occur at 8/3, but if it actually does have a minimum or maximum, it occurs at this value. So let's plot the function that we are looking at here, which is so. So if we plot, and this is a chapter, it's good to plot stuff. So you have x, I'm going to use x as the variable, square root of 4 minus x. Okay, let's see if that's what I was doing. X times the square root of 4 minus x. Okay, let's graph it. So there it is. And you can see at x equals 8/3, which is right there, that we do have a local maximum. So it turns out in this case, this critical number is a local maximum. You can also see that the slope approaches negative infinity at 4. We said that was where the denominator went to 0, and therefore this is a case where the derivative is undefined. And then the curve just kind of, after it peaks, it goes back and it'll just keep going down. So you know, from this information, we know that there's not going to be any other places thing loops around and changes direction. It's always it's going to continue to go in that direction. Okay. So that's an example of one that's not just a polynomial. Okay. So before we do this, here I'm going to let you guys work on this one. So first question is find any critical numbers for f of x. So let's do that first. So what does that mean? It means take the derivative of that function. Are there any values of x where that derivative does not exist? Answer that question. Solve, set the derivative equal to 0, find the values of x where the derivative is 0. Is that value of x inside the interval that's shown, -2 to 1? If it is, and the derivative is 0, then this critical number. That's the critical number. In this case, there's going to be one critical number once you take the derivative set equal to 0. Then we'll use that information to answer the second question, which is locate the absolute extrema of the function. We haven't defined what the absolute extrema means, so we will we'll do that once we. So it shouldn't take too long. It's an easy derivative, but I'll give you a minute here to think about what you were doing. Okay, so that's all there is to it. You take the derivative, you look at that, and you say, okay, it always exists. It's a polynomial. 2x plus 2, doesn't matter what the value of x is. You don't divide by 0. You don't have anything weird happening. So it always exists. So that's not going to give me any critical numbers. I set it equal to 0. I get a critical number at -1, which is inside the interval, and therefore we can say x equals -1 is a critical number. Okay. So how can we use that to answer the question here? Or what is the local extrema? So let's plot this function and explain how it works. So the function was x squared plus 2x minus 4. X squared plus 2x minus 4. So it's a parabola like that. So let's copy that over to my smartboard. Where's my camera? Here we go. And I'm going to zoom out just a little bit in that direction. Okay. Okay, so there's the function. Let's look at it. So the interval, and I forgot to, let's see, this must be, what's the scale here? I cut that off. Okay, so this is -1, this is -2, -3, 0, 1, 2. So what I defined in the problem was I wanted to look at the interval from -2 to +1. So the only part of the function that I'm interested in is this part. So when I mention the word absolute extrema, it's the most positive and most negative value for the function on the interval. So if we look at this function, what we found out was that at x equals -1, we have a critical number, and it turns out this would be a local minimum. It's also the smallest value for the function on the interval because it starts here and then it goes down to the lowest value and then loops back up. So in this case, the most negative number is going to be the value of the function here, whereas the most positive number is actually going to occur here at the end of the interval. So there's 3 places that you can have the biggest or smallest number, the most positive or most negative number. It can occur at the beginning of the interval, at a critical number within the interval, and at the other end of the interval. So what we do is we use the endpoint, we evaluate the function at the endpoints. So we're not drawing the graph, we're doing this without looking at the graph. What you're going to do is you evaluate the value of the function at the ends of the interval at any critical number within the interval, and then you find out which is the biggest number, most positive number, and which is the most negative number. So that's what we're going to do. So let's add a page. So we'll say to find absolute, meaning the biggest on the interval, to find absolute extrema on an interval, meaning a range of x values, evaluate the function at both endpoints of the interval and at any critical numbers within the interval. So what we're going to do is we're going to evaluate, in this case, we're going to evaluate the function at -2. We're going to evaluate the function at +1. And we're going to evaluate the function at -1. So these are the endpoints. And this is the critical number. So let's write down the function so I don't forget what it is. F of x equals x squared plus 2x minus 4. And so we're going to add a page here. So f of -2 equals -2 squared plus 2 times -2 minus 4. F of 1 is going to be 1 squared plus 2 times 1 minus 4. And f of -1 is going to be -1 squared plus 2 times -1 minus 4. So go ahead and calculate what those are. Make sure you, when you square -2, make sure you do that correctly. We already know from the graph what should happen, but we're not. Let's see what we get. So how many people are worried about North Korea? Or is it like, I don't really, can't do anything, so I'm not worrying about it? It's an interesting. How many people are worried about Donald Trump? Yeah. Yeah, Kim Jong-un, whatever his name is. They're both clowns. It's like the, yeah. Okay, so let me ask somebody here. Hannah, what'd you get for the first one? Hannah, what'd you get for the first one? -4? Okay. Savannah, what'd you get for the second one? Don't know. I'll come back to you. So work on the second one. So Asia. Negative what? -5. And this one should be this one here. So it's 1 plus 2 minus 4. -1. Yeah. Okay. So what we can say is that the absolute minimum is something, and the absolute maximum is something. Okay. So look at those numbers and see if you can figure. So Lexi, what do you think the absolute minimum would be? Yeah. So the absolute minimum is -5 because it's the most negative number, and the absolute maximum is -1. Okay. So in this case, the absolute minimum was at the critical number, and the absolute maximum was at the right interval. And you can see that on the graph. You know, this would be your absolute max, and this would be your absolute minimum, which is what we just figured out. So that's how, if you have a problem asking you to find the absolute maximums or minimums, the procedure is to find the critical numbers, if there are any in the interval, then evaluate the function at the endpoints as well as the critical number. These are the only places that you can possibly have the maximums or minimums. So then you just compare them, and the one that's most negative is the absolute minimum, and the one that's most positive is the absolute maximum. So that's what I just said. There's the guidelines. They're in your book. I'm not going to go. That's what I just told you. So why don't you guys try that one out? So what you're going to do is you're going to take the derivative. It's defined, so you don't have to worry about that part. Find the values of x where the derivative is equal to 0. You'll have to factor, do some factoring. It should be two x values for where the first derivative goes to 0. And then what you do is you will evaluate the function at the endpoints, which means that x equals -6 and x equals 3, and you'll evaluate it at the if they're within the interval, the two critical numbers. So that'll give you 4 numbers, most likely, and then you rank those. The one that's the most negative is the absolute minimum one, and the one that's and you can actually here's the procedure, and that was very handy. So there's the procedure you follow. And when you factor it and you set it equal to 0, you should have a common constant that you can cancel out, to simplify it. So it's x squared instead of 3x squared. You can see that if I take the derivative, I'll have 3x squared. But every term will be divisible by 3. So simplify it before you factor it. Don't factor it as 3x squared and something else. Get rid of it. Not get rid of it, but simplify it. That just makes the factoring easier to do. It looks like we're almost out of time. So we might have to finish this. We'll at least do the derivative part. We'll at least get the critical numbers, and then we'll do the rest of it on Thursday. By the way, next Friday, we're going to have a guest speaker come. All the governor's school students are going to participate, as well as any community college students that are interested. She's a researcher who does research on sleep and dreams, and she's doing some kind of lecture at the osteopathic school in West Virginia, and somebody who's a member of the group that's sponsoring her is a friend of mine in the band, also from West Vaco time. And she said, would you guys be interested in having her come and talk? So that's going to be, instead of physics on next Friday, it'll be a guest lecture. The physics test will be the following Monday. Okay, so I'm not going to do both calculus and physics next week, even though I probably should. I'm going to wait to give you a little more time, so you can put that on your schedule too. So it's a week from next Monday. It is. I probably would have figured that out when I got to this point. I couldn't factor it. Yep. So if you factor out, if you divide everything by 3, you get x squared plus 4x plus 1. Actually, that's not an easy one. That actually just still doesn't factor out easily, does it? We'd have to use completing the square, so we'll talk about that on Thursday.